So, hello everybody, welcome to my session. My name is Viktor Mukha. I will be talking about AIDL Hardware Abstraction Layer by example, how to use hardware from Android applications. First, a couple of words about myself. So, I have been working on Android Automotive since 2019. I am leading ASP-related research and development at ParadoxCAD, and I'm also contributing to Covisa initiatives. I have been talking before here on DroidCon with two different talks. One was about custom launcher, and the other was about ASP development environment. So, we all may have seen these beautiful Android architecture pictures before. They may look a little intimidating, so I don't want to talk about these today. Let's be honest, we all want to see GitHub code. So the motivation of this talk is basically we need more open source examples of hardware abstraction layers. So thank you, Chris. I don't see Chris where he is. Two talks before, he was talking about open source and exactly this problem. We don't have enough open source hardware abstraction layers to use as our examples. So we all look like that when we're trying to work with one. So why is that? Because hardware abstraction layers are usually developed by the vendors of the hardware behind closed doors. So we're lacking good examples. Some of them wouldn't compile with the newest Android. Some of them are just hello world examples, which are not particularly useful. And some are maybe even too complex for our purposes. So let's fix that. The agenda for today, I will be talking about connections first. How do we connect the hardware? Because we will be talking about this particular project. This is a Samsung S5e tablet, and we are connecting a specific hardware here. I'll get to that right now. Then we will talk about how to use the hardware itself from the Android application. And this will lead us to the discussion of hardware abstraction layers, system services, and exposing the APIs towards the applications. So first, let's talk about connections. So this is the hardware we have been experimenting with. It's an Infineon 60 gigahertz radar sensor. And to be more precise, we have been using these demo boards, which have this little sensor mounted on them already, and we have USB connector. So we have this tablet. How do we connect this demo board to the tablet, right? Well, you might think if you connect a keyboard to this tablet, it works, right? Would it work with the radar? Well, the first thing we did, because we already had experiments on Linux machine, we thought, OK, we can just use some intermediate entity between those two and basically run some machine learning in Python on Raspberry Pi, connect the sensor to Raspberry Pi, and then communicate the events, like gestures or something similar, to the tablet via MQTT or any other means. So this, in fact, has been implemented, and you might have seen it a couple of years ago on DroidCon. But then we thought, well, we know Android, we know ASP, maybe we can connect it directly. Android can do it all. Another option, actually, if you would have been working with the sensor as a hardware vendor, you would actually be integrating it with the hardware directly, and then you would use something like SPI. But I didn't feel like disassembling the tablet and looking for the particular pins to solder to. Most probably, I wouldn't find ones. So, however, it's possible, right? So Pixel 4 actually, in fact, had this pretty much the same sensor, Infineon 60 gigahertz radar. It used to be called Project Soli. and you can find more information about it following these links. So let's connect directly and get some data. How do we communicate to the sensor from Android app? So first, if you look at the USB documentation in Android, you can find that, yes, you can connect peripherals to your Android device. It will power it. It will be a host in this case. And you can even use USB Manager on the Android runtime Java layer, where you can communicate via serial protocol directly. And if you know the serial protocol of your device, this might be actually a great solution. And there is even a library on GitHub which makes it easier. To test if this would work for you or not, you can simply download this app, Serial USB Terminal, from Play Store, and see if your device, your serial device is actually recognized, and you can see it directly. So this would be a beautiful solution because this makes it portable. So you don't need to mess with the system. The only dependency for you is Android SDK, and it would work on all devices. So let's see what we are working with. So looking at the official SDK for this radar, it's called Radar Development Kit. We realize they have C, C++ APIs, Python APIs, and MATLAB APIs. So what options of the integration do we have here? So first, as I mentioned, we could re-implement the whole serial protocol via USB Manager on the Java layer. However, if you look at this SDK, it's very complex, and just to find the actual protocol out there and reverse engineer it would take you quite some time. So option number 2, use Python or MATLAB on Android. Possible? I wouldn't do that. We're left with C and C++, which kind of makes sense. And there we still have different options. So one, we have the option of writing an app using NDK and simply communicating via NDK. The other is to integrate this Infineon SDK really deep into the system. So let's start with NDK. For prototyping purposes, perfect starting point. So we create an empty app, let's say with Compose and NDK. We can integrate the Radar SDK via NDK into the app. There are different options to do that. I won't go into details here. It doesn't really matter. And then you design and implement the GNI layer between your SDK, Infineon SDK, and your application. And it could be as thin as you may need it, right? So you don't have to expose the whole SDK to your app. So we tried that, and you try to connect. You are getting error 13, permission denied. Kind of expected, but why exactly? So let's start from the beginning, trying to understand what's going on. If you look at the logcat, you can see the K workers, the kernel logs. You can see it sees the new USB device. It recognizes vendor ID, product ID, it's Infineon. You can even see CDC ACM, which is the kernel module for serial over USB, that it even enumerates the device as TTY ACM0. And then in the blue, you can see some Java stuff with the USB host manager going on. If you don't see that, one problem you may have is a bad cable. That's what we had. And it took us some time to realize that such U-shaped adapters are sometimes, most of the time, don't have the data lines in them. Beware. So yes, we have the Linux device driver, and it works, right? So it enumerates our thing. It's dev TTY ACM0. So make sure you get there. So if you don't get there, then you have to take care of that first, right? So you have to either write a custom Linux module, kernel module, or get one from the vendor, but you somehow have to expose it to the user space first. Then the next step, right? So we're still like on a Linux level. So how do we talk to this def entry? So we call open. It's a file, right? So in this case, it would be using Bionic in Android, which is libc implementation. So one of the return codes, if you look at the documentation, is eaccess13. This is the one we're getting. And there's a lot of reasons you could be getting that. So how do we get the privilege? One thing which is important to remember is that Android is not only C Linux, it's also normal Linux with groups and users. So the first thing we have to do is to check, does a user from an application have access to the device? And in fact, if we go to this device and ADB shell and look at it, you can see that only root has access for reading and writing to this entry. So on normal Linux, you would often see a dial-out group access to this entry. This was not the case here. To quickly test if this is exactly your access problem, you can change the mode to world readable and writable. We did that. We're still getting error 13, but this time due to EC Linux. However, I want to mention how to fix this properly without having to every time change the mode of your device. So the proper solution it involves a service called ueventd. In it starts the service, and this service is responsible for setting permissions on def entries. So configuration for that is usually found on device, in system, etc. ueventd rc. And this belongs to device configuration. In our case, well, with Lineage, it's here. And you can basically add a new line there saying, hey, everything dev TTY-SCM has to be read, rolled, writable. And maybe it's a bad idea to expose it to the world. Usually what you see in this file is entries exposing to system, user and system group. So in this case, as you can see in the latest option, our app is already getting into territory where it makes sense to make it a system app. Then we get into EC Linux, and won't go much into detail here. It's too complicated. Let's just make it permissive and look at the violations. If you can decrypt those are, we're trying to read the root entity, we're trying to open the def, we're trying to get attributes of def TTY-ACM0, and all of that is forbidden. So we can fix that. But let's come to it later. Let's just keep it permissive. And the last but not least, you're trying to connect, but still getting an operation not permitted, this time with some weird socket stuff. It's not obvious, but you also need users permission in your Android app manifest for the internet, because it's a socket. Finally, we have succeeded opening our sensor. It's connected. We can get information from it. Also know that the USB manager Java stuff, Android runtime stuff I was talking about before, we don't have to touch it. We don't have to request any permissions. It just works. Let's recap. So we have been using Android SDK in the application. So we have the kernel driver already, so that wasn't the problem for us. We had to change something in the device with the permissions. We had to fix the C Linux violations and add something to the app manifest. This is totally fine for a demo. More than fine, it's perfectly working example. You can make your app system app. Everything's great. Is it good enough for a product? Let's refactor a bit. So I would say everything what needs the app to be the system app can just go to some kind of a native service. And we just leave the rest in normal Android application. And now, we're not talking about hardware abstraction layers still, right? And the talk is about hardware abstraction layers. So do we need it? For that, let's actually start with trying to understand why HALs even appeared. Logically, Google cannot know all the hardware in the world in advance, so they basically define certain APIs towards the hardware, and then the hardware vendors must implement all the required APIs listed in a so-called compatibility matrix for a particular Android release version. And some of them can be required, some of them can be optional. So basically what vendors do, they go to these hardware interfaces, they find the version which they need to implement. This is all specified in this compatibility matrix, and they implement it. These are some examples of the HALs, very old picture. Sorry for that. So let's come back to our radar. Do we need a HAL there? Well, ideally, if we look in hardware interfaces, we would have found one, right? This would have been something like radar. But there is no such interface in there because there's no standard concept how radar should interact with the Android system, right? So we can define our own custom HAL interface, but why would we do that? So first, and I think the most important, is that we decouple the logic of the radar, whatever we do with it, with the data, from the hardware specifics. And also, we are enabling this mechanism of reusing and potentially enabling the upstreaming. So imagine you have multiple vendors already using this hardware abstraction layer interface and multiple applications or system services using it, and it's worldwide known, and the concept kind of UX is already established, then you can actually potentially upstream it. Also, it's the convention in the clean solution. So you encapsulate all the Linux policies there, and you keep the interface simple because, well, different vendors have to implement it in the end, or you have to implement it for different hardware devices. So yes, I would say we need a HAL. At that point, I would jump to a demo. We have released a couple of repositories on our GitHub. It's all public, MIT licensed. And let's start with the main ones, which is the local manifest. Very simple. I hope you can see it. Is it large enough? Is that better? OK, so this one just has the list of repositories you would need to kind of reproduce what I'm going to show today. The vendor stuff is the HAL. The packages stuff is the service, which we'll talk about later. And this is some external dependency for the service. So in this repository, you can find all the instructions, what you need to do to reproduce this whole demo setup. So it's all open source, MIT license. Do with it whatever you want. So the next repository is the HAL. Let's take a look what's inside. Again, README with some instructions, tips and tricks, what you can do with it, like implementing dumpsys, for example, very handy thing, or like how you can quickly test it without having to flash the whole device again. So if we look at the folder structure, usually it's under AIDL, so this is a new thing. And the interfaces, the hardware abstraction interfaces I was talking about, is this. This is our main interface from the hardware to the service, let's say. And it's very simple here. Subscribe, unsubscribe. We have a data listener callback, which is giving you the frame data. The frame data is a float array, and it's specified, the size of this float array is specified by the sensor configuration. So there is many other things to talk about here, like WinTF stability. What is this stable AIDL? Why AIDL? And so many things that I would say it's a different talk. So simply take a look at the code. You can find a lot of interesting examples here. And then this interface has to be implemented. So here in the default implementation directory, you can find the actual service, which is essentially calling service manager at service and exposing this hardware abstraction layer implementation to whoever would like to use it using the binder. So this one's using NDK backend. And then you have the actual implementation. So the radar HAL class here is inheriting from this generated class, which is generated from the AIDL for NDK. So this is a very quick overview of the HAL. So let's proceed with the presentation and talk about system service. So can we talk from our application directly to this HAL? In fact, we can, because it's AIDL. We can simply use Java-generated sources and get along with it. However, this could be a good idea to abstract it to the service. So why? Generally, applications don't want to be depending on anything but Android SDK. Maybe a little bit vendor extensions if we're talking about custom hardware, so that you can develop them outside of ASP.tree. I mean, there are many pluses, many pros there, right? Also, we want to keep hardware abstraction layer interfaces simple, right? So we don't want to force all the vendors to implement 25 different algorithms for us. We want to just tell them, OK, expose the actual device to us, and we'll do this in the framework somewhere. So the system framework can then add more complexity. It can manage permissions. It can manage multiple sensors, multiple applications. And it would contain a common logic, such as using AI to do some magic with the sensor, right? So for the service, let's jump back to the VS Code. You can find the repository in packages services. And here again, README with some interesting information, tips and tricks. And the service itself is basically the idea of the service here. We're getting this raw data from the HAL, and we are putting out a stream of pictures instead. So from this raw data, in this case, using TensorFlow Lite, LiteRT library, we are basically pre-processing the data, reshaping it to output some images. And what you can also see here is in radar HAL manager. Manager is like a typical pattern in ASP or in Android to hide the AIDL complexity from you. So you don't have to pull all the AIDL files, generate the code from them, and inherit and do stuff. You can simply use the managers for that. So what's interesting here also is that the service itself, again, exposes AIDL interface towards the apps. And again, so this is very similar interface. It's basically subscribe, unsubscribe. You provide it to the listener. You get the image. The image is array of bytes. And then the last but not least interesting part here is the manager. So the manager, again, for the service this time, not for the hardware abstraction layer, but for the service. We're trying to hide the complexity, and the only thing we're doing is basically outputting the image flow for the apps. OK, so this is the example of the service. Let's talk a little bit now about exposing this service to the applications. To do that, you basically need to take this manager class I've just shown you, pack it as a jar, remove all the useful code from there, and replace it with stubs so that the developers don't depend on it. And distribute it. There are multiple ways to do that. The most popular ones are vendor SDK or SDK add-on, or you can distribute multiple jar files manually or via some Maven instance. Same idea. You use the stubs during development. They get substituted at runtime running on the device. There was a great talk on DroidCon Berlin in 2023 from Nikolai Pahomov about this exact problem and how to expose APIs from the system to the applications. Check it out. So I will not dive into details here. Again, now we're coming to the app. Let's see the code for the app. It's a very simplistic Compose app. So the most interesting part is happening here. So we're basically calling this image flow, collecting this image flow from the manager, transforming this byte array into something useful. We already know the dimensions and everything configured in the sensor, and then displaying it. So let me now try to show you the actual demo running on this tablet. So I have to enable wireless debugging again so that I can show you the screen of the device, otherwise it's a little too small. Let's see if it connects. Not yet. Now it shows that it's connected, that it should be there. Okay, so we're seeing the screen. So this is the Radar demo app you would see. And the demo effect, obviously, takes forever. Doesn't work. That's why we have the buffer. Yes. Okay, so this is what you're supposed to see. It's like one of these predators. When you don't move, it doesn't see you. When you do move, it actually starts seeing you and showing you some information. So with this data, you can actually do some training and detect gestures. So when you do like swipe left, swipe right, or presence detection, a lot of interesting scenarios. But this is basically it. So the whole demo is that this app is now talking to the service is talking to the HAL is talking to the sensor. Okay, we're getting to the summary. My main point is let us talk about these things, let us share more, let's make it open source. Whatever projects you might have, which are your personal projects, are not related to organization, or maybe part of organization but could be open sourced, do it, let's talk about it, let's share it so that we don't look like this guy on the first slide. Also, I want to tell you that don't take shortcuts. You probably do need all of these layers in Android. They do make sense. And again, just to recap, this is the whole chain of things we were doing. We got the kernel and the driver. We created a HAL service, which exposes HAL interface. And this interface is used by the system service via AIDL, which is again exposing another AIDL interface via a manager jar towards the Android application. So in this case, your Android application is really normal Android app, didn't need any specific permissions, although you could define ones. The system service is on the system partition, the HAL service is on vendor partition. Everybody's happy, everything is independent. My call to action to you, go to GitHub, start the repository, use it, ask questions, share your experiments. This is the starting point. This is the local manifest repository. It has a README. If you follow it, you should be able to reproduce exactly that. You can get yourself an Infineon sensor if you like. And with that, these are the contacts. I would like to also mention Chris Simon's presentation. and the initiative about AOSP devs. Do check it out. This is exactly the part, right? So you get the code. The code is there on GitHub. It's perfect. But open source, as Chris said, it's not only about the code. It's also about the community. So the community is there. For these things, this is the place to go. And you can also hit me up directly. These are my contact details. So with that, thank you very much. And I'm open to any questions.